In production, MCP is more than a protocol. It becomes the integration layer between AI clients, tools, and enterprise systems. In this module, we'll look at where MCP creates value, how deployment patterns differ, and how safety, scale, and maintainability shape production design choices. You already have the core MCP mental model. An AI client talks to an MCP server, and that server safely exposes tools, resources, and prompts from backend systems. Now we'll apply that model architecturally across CRM, ticketing, code search, analytics, CI/CD, and enterprise knowledge scenarios. In production, an MCP server acts as the controlled bridge between an AI client and the systems that run the business. Rather than giving the model direct access to databases, ERP platforms, or internal APIs, we expose carefully defined tools and resources. The server handles authentication, validates inputs, applies policy, and records what happened. That standard contract reduces one-off integrations while keeping ownership boundaries intact. The goal is not unlimited automation. It is safe, scoped capability that supports real workflows without bypassing governance. One common MCP pattern is controlled access to the systems employees already use every day. In a CRM, that might mean summarizing an account before a sales call. In ticketing, it could mean finding related incidents or preparing an escalation summary. In ERP or admin tools, it might check order status or vendor details. The main point is control, strong authorization, tenant isolation, and a clear separation between read-only access and actions that change business records. For engineering teams, MCP can make an AI assistant a safer interface across the toolchain. Instead of guessing from isolated files, the assistant can search code, trace dependencies, inspect configuration, and identify owners. Repository access can support pull request summaries, changelog drafts, or test impact analysis. C and deployment integrations add live build status, pipeline logs, artifact versions, and release gates. The critical boundary is write access. Actions like rerunning a pipeline, merging code, or deploying a release need explicit permissions, approvals, and audit trails. Another major pattern is helping AI clients work safely with company knowledge and data. This could include searching internal docs, policies, runbooks, and decision records. It could also include exploring database schemas, generating read-only queries, or investigating metrics in BI tools. The value is speed. People can ask better questions without manually jumping across systems. The risk is that these servers may touch sensitive records, expensive queries, PII, or business-critical interpretations. So the production model is not connect everything. It is controlled access, scoped permissions, cost limits, auditability, and clear boundaries around what answers mean. Think of the MCP server as a secure facade, not a shortcut around your application architecture. The model makes a tool call, and the server translates it into approved API requests against systems you already trust. Existing authentication, authorization, validation, business rules, rate limits, and audit logging should still apply. In most production designs, direct database access should be rare, tightly controlled, and preferably read-only. MCP's value is translation. It turns flexible, AI-friendly requests into deterministic backend operations, then returns validated results the client can safely use. Local MCP servers are especially useful when the user is a developer. They can search code, read local files, call workstation tools, and support quick experiments without waiting for a shared service to be deployed. That speed comes from proximity. The server can see context that a remote system may not have. But proximity also creates risk. If local servers can touch shells, secrets, repositories, or credentials, they become harder to monitor and govern consistently. Use them for low-friction development, but add constraints before treating them like enterprise infrastructure. For shared production capabilities, remote MCP servers are usually the stronger pattern. Instead of every AI client carrying its own fragile integration, clients call a managed service that connects to systems like CRM, ticketing, knowledge bases, and operations tools. That central point lets the enterprise enforce identity, authorization, audit logging, monitoring, rate limits, and policy consistently. It also makes tool behavior easier to standardize across teams. The trade-off is infrastructure responsibility. Network latency, uptime, tenant isolation, security boundaries, and safe rollout of updates all become design concerns. Hosted MCP platforms can be a strong accelerator. They package hard operational pieces such as hosting, authentication, monitoring, scaling, and sometimes a shared tool registry. That lets teams focus on building useful tools instead of running infrastructure. The trade-off is control. You need to understand where data moves, whether audit logs can be exported, how identity integrates, and what happens when you need custom policies or low latency. Treat managed MCP as a governance decision, not just a convenience decision. Choose it when the platform matches your security and compliance needs. Deployment choice comes down to control, speed, and shared responsibility. Local servers are useful for individual developers, prototypes, and sensitive workstation context, but they do not scale governance well. Remote enterprise servers provide shared capability, stronger policy enforcement, and production reliability, with more operational ownership. Hosted platforms move faster and reduce infrastructure burden, but require trust in the provider and offer less direct control. In practice, many organizations blend all three: local tools for development, remote services for business use, and managed layers for monitoring or registries. In production, MCP, permissions are not just yes or no. Think of every tool as sitting on a risk ladder. Reading may feel safe, but it can still expose secrets, regulated data, or another tenant's records. Writing raises the stakes because the agent can alter customer data, tickets, code, or business state. Then there are actions with real-world consequences: deleting, deploying, purchasing, or sending messages outside the company. Those need stronger controls. The practical pattern is to classify each tool by impact, then attach the right approval path, audit trail, and rollback plan before the agent can use it. Safe tool design starts with narrow tools. A tool like Create Support Ticket is much safer than a generic HTTP executor because the model can perform only one well-defined job. From there, constrain every boundary with strict schemas, allowed values, validation, and output limits. Authorization must be user-scoped, so the model never gains powers the user does not already have. Finally, separate read-only tools from write-capable tools. Reading data may need logging. Changing data needs stronger checks, approvals, and audit trails. High-risk agent actions should never be treated like ordinary API calls. Before a deployment, billing change, customer message, or destructive operation runs, the request should pass through a policy check. Low-risk actions may be allowed automatically. Riskier ones may be denied, require user confirmation, or require privileged approval. Every step should create a durable audit trail: who initiated it, which AI client acted, what tool ran, the inputs, outputs, time, and final decision. And because mistakes still happen, production systems need rollback, remediation, and evidence for post-incident investigation. The core lesson is that production MCP design is unified. Start with valuable use cases, choose an architecture model that fits your control and scale needs, then define risk boundaries through scopes, authorization, validation, approvals, and audit trails. When these decisions reinforce each other, MCP servers can safely connect AI clients to real systems. Next, we move from patterns to lifecycle.